follow-up questions or question about the homeworks? Is that something we should talk about before starting today's lecture? No? Yeah?
Could you briefly sketch out the rule for the sequent calculus rule for the OR with the arrows down?
Ah, good question. Okay. So the question was, if I have a rule like this, if A or B, I can use that, assuming A, I get to use C, then I'm allowed to use C, and this was our alternative version of OR elimination, okay? And the question was, what does the sequent calculus rule that corresponds to that look like? Okay, any thoughts? Anybody look at this problem? So we have two people who worked on it, Sylvia and me. Okay, so I worked on it for a few minutes, and yeah, you worked on it. What was your answer?
The best I came up with involved a D, which I wasn't sure was the right choice.
Yeah.
Okay, so do you want to tell me what you thought about?
Well, this is like basically everything has to be on the left. It's all over.
Yes, because these are all down arrow, everything has to be on the left, right? So that's okay. But this happens in the context of a bigger proof, right? Where you're trying to do this, right? So that's where the D comes in. Okay. So then now, what do we conclude from there? Okay, so we should have a sequence somehow where we have D on the right-hand side, right? And now it starts to break down, right? Okay, well, we always have a gamma. Okay. So far, hardly any controversy can erupt. Okay. Now, we're supposed to be able to use A or B. So that should be over here, right? Okay, so we don't really, when we start, we shouldn't have anything else, should we? Right? We should just have A or B because we want to apply elimination to that, right? Okay. So, all right. So then what can we say about here? Okay, well, we still have A or B, right? That's our principle. Once we have something, we'll always have it for the rest of the proof. So that's not a question. There's two branches, so we should probably have two premises. All right. In both branches, okay, so now it becomes really tricky, right? I want to say we're still trying to prove D, because C is on the left-hand side, so somehow we should still try to be proving D. Okay, so at this point I got stuck because, well, maybe in this branch we should have A, right? So we should have A as an assumption. And here we should have B as an assumption. But how do you represent the fact that from these assumptions we can, we can deduce C as a conclusion, because the only thing we're allowed to write on the left-hand side is things that we know.
Conjoin it with D on the right side? Conjoin it with D on the right-hand side?
We could write C and D here, but that would mean it would be an up arrow, right? You would be constructing a verification of it because it's on the right. Okay, so that doesn't work.
Not C, if we were classical.
Not C, okay. Maybe if we're classical, and also then it's not really clear what we mean by right on the right and the left. So maybe there's an out there, I don't see it. So I came to the conclusion at this point, okay, there is no sequent calculus rule. Okay, that expresses that, okay? And so that means that this rule is a bad rule, right? Because for all the other rules, we have a perfect correspondence. They have a certain shape and form. There's a logic to it, right? That you only work with introductions from below, eliminations from above, okay? And whenever you have a proof, you always, that you're trying to construct, you're almost trying to construct a verification at the bottom rather than that something can be used. So we would need to generalize our sequent calculus to something different in order to be able to capture the contents of this rule on the left. Okay. So is that the conclusion you came to?
Yeah, I kept thinking it doesn't make sense to be able to write a rule like this, but
Yeah.
I hope there was a different answer.
No. You got the right answer, right? There is no rule in the sequent calculus, so we'd have to generalize the sequent calculus to figure out how to do it, right? So, okay, good. So, I'm collecting reasons why this rule is bad, right? So I just added one more, okay? Other questions? Yeah? Yeah.
The same on the bottom. You're using a kind of a shorthand way, I assume? I've been trying to sort of decode it as we go along.
Okay, so what shorthand? I mean, so the reason. Okay, so in these lectures and also in Bob's lecture, we use this notation for natural deduction. And so I felt compelled to make a different notation so that these things are distinguished. So this is natural deduction, and this is sequent calculus. And I could equally write Royal turnstile here, okay? But then I would need to distinguish some other way. Then I would write above the turnstile, okay, this is natural deduction, this is sequent calculus. And that gets tedious, okay? So there's no deeper meaning to it than that. Okay. Yeah.
What was the source of the rule that you used in that what could not be included in the rule?
A student. No, I mean, you think about the rules, you try to figure out, and then, the question always comes up, well, what about that rule? Could we have that, right? And it doesn't seem to fit. In some ways it fits, because it still satisfies the subformula properties, but in other ways it doesn't fit. And one way to see that it doesn't fit is that it doesn't have a corresponding sequent calculus rule. Yeah. All right. Yeah.
For the temporal logic sequent calculus one,
Yeah.
it seemed like there were some arbitrary choices, and which ones were down arrows and which ones were up arrows.
Okay. Are there arbitrary choices? Okay. So let's think about that. So to prove circle A at type t, you have to prove A at time t plus 1. Okay, so question is, should this be up arrow or down arrow? Should be an up arrow. Why should it be an up arrow? Yeah, that's kind of a second order reason, but there's a very simple reason. This is an introduction rule. And the introduction rule constructs verifications. And constructing a verification means that you have to go from up to up. And what's the elimination rule? Well, if you know A at time t, then you're allowed to circle A at time t, A at time t plus 1. This is the elimination rule. So what should the arrows be? Down, because this is how we use the knowledge of circle A. And so the elimination rules are the down arrow. So I don't think there's any ambiguity.
But why couldn't this one be up also?
Okay, so if it's an up, that would be wrong, because to prove A, you would have to invent a bigger proposition. So the premise would not be a subformula. Yeah, so the propositions here is this and this. So you couldn't use this as a verification rule because you'd have to, the meaning of A would depend on the meaning of a larger formula. So you can't use the up arrow there. Okay? All right. So, okay, so I want to do two things today. First, yeah.
Well, what if you made it the other way around, and then you knew that T was going down? The one on the right would be up arrows, and the one on the left would be down arrows.
I mean, these ones would be down arrows?
Yeah.
Okay, again, if a down arrow, you need to assume you know that, and then this has to be a subformula of that it would not be the case.
But you have the number gets smaller.
Oh, the number gets smaller. Well, the judgments, when we consider these directions, we don't consider the judgments, we consider whether we break down the propositions because we want to use the rules to explain the meaning of propositions. Okay, so the fact that time gets smaller, that might be something different. I haven't thought about how that might fit. It's interesting, there might be something to be said, but I haven't thought about it at all. So we're just thinking about when we have these rules, they're introduction elimination rules for propositions, so we focus on this part. Okay. All right, so what I want to do today is first I want to actually talk to you about how to prove properties about systems and complete this kind of a picture that I started to paint about how sequent calculus and natural reduction and verifications are related to each other. Okay. So let's skip it to this part. Okay, so we have written the natural reduction so far with some assumptions up here and a conclusion here. And the natural reduction sits in between, and sometimes we gave it names for these. Okay, so in other lectures you have seen a localized notation, which I'm going to write like this for these verifications. So I'm going to have A up here, and this is gamma, and every formula there is annotated with one of these down arrows because we're looking at verifications. Okay, so because this is a hypothetical judgment, and this is our notation for hypothetical judgments, is completely consistent. It's just a one-dimensional way of writing things which are two-dimensional over here. So it just makes it easier for me to write. But it's exactly the same as this. Okay, so there's no semantic difference between. And sequent calculus I still write like that. Okay, so now what I'd like to prove is that verification and sequent calculus are actually the same. So this intuition I had when I constructed the sequent rules, I want to express this as a theorem and verify that it's really true. I didn't make any mistakes. Okay. So there's two directions. One direction, if this holds, then this, and the other direction from here, you can go back to here. So I'm going to just do one direction, and what I want to prove is the theorem. Okay. So if gamma down proves A up in natural deduction, then in the sequent calculus, we can prove A. Okay, so now how do we prove theorems for complete, fully specified deductive systems? Okay, we do this by knowing what other possible proofs are, and we're doing an induction over the structure of those proofs. And we do that by considering all the possible cases, the way the proof could be constructed. We have to make sure that we know how to construct this proof from the parts that we have here. Okay, so I'll walk you through a couple of cases, and then we'll see how to actually go about how this kind of thing works, just so you see that how to reason about the system globally. Right? We have done these local tests so far, but now we're actually doing something global because we're fixing now our system here entirely with all the connectives, and then we're trying to prove that. Okay. All right. So.
The other theorem holds only on one side, only from natural deduction to sequent calculus property.
Okay. So there's a second theorem which goes back from here to here, but I don't want to prove that. I want to, otherwise I could spend, of course, the whole lecture just showing how to prove these things, but I just want to focus on one. This from here to here is the easier direction, so I'm going to the more difficult one. Okay. All right. So now we're looking at the possible cases for this. Okay, so let's give this thing a name. Let's say this derivation is, let's say it's d. Okay. So one possibility for d is that it looks like this. we have gamma down proves A1 and A2, and we have a verification of that, because in gamma down we have a verification of A1, and in gamma down we have a verification of A2, and let's call this derivation here D1 and this derivation D2, and this was done by end introduction. Okay? So when we're doing induction over the structure of a derivation, okay, we can apply the induction hypothesis to the subderivation. So we can apply the induction hypothesis here and the induction hypothesis here, right? Because we're considering, you know, the structure of the proof, structure of this derivation here, as something that we do induction over. Okay. So if we apply the induction hypothesis to D1, what do we obtain? Yeah. So we get is from gamma we can prove A1, and this is by induction hypothesis on D1. Okay? We can apply the induction hypothesis to D2, so we get gamma proves A2, and we get this by induction hypothesis on D2. Now what do we have to show in this case? We have to show that gamma proves A1 and A2 in the sequent calculus. Okay, how do we get that? Yeah, so then gamma proves A1 and A2 by the right rule for and in the sequent calculus. Okay, and all the right rules follow the same pattern. All the introduction rules, I should say, follow the same patterns, because if you remember, globally what we did is introduction will correspond to right rules, and elimination rules correspond to left rules, turned upside down, right? So the cases in this proof where we use introductions, they're going to be fairly easy because they all follow in the standard way, because the rules are mirrored exactly. Okay, everybody on board with that part of the proof? Okay. So where do things become hairy? Yeah, with elimination rules, obviously. And in fact, our theorem doesn't say anything about elimination rules, right? So at this point, we realize our induction hypothesis is not going to be strong enough, because when we come to this case, D is gamma down proves A up, because gamma down proves A down. And this is some other derivation D prime. Okay. We can't apply our induction hypothesis to the subderivation because it's a proof of A down, and all we know here, all we have stated so far, how to handle A up. Okay, clear? Okay, so we're stuck. Okay, so then what we do is, okay, that's the first part. We need to generalize our induction hypothesis. We need to say something about what happens with A down. Okay. All right, and now comes the really creative part in this kind of proof. Okay. What is the right part of the induction hypothesis when A down holds? Okay. Now, the very first time I did this kind of a proof, some years ago, it took me many hours to figure out how to do this. It seems completely obvious, right? Because we translate the right rules to right rules, and the elimination rules to left rule turn upside down, right? And we were very careful to do it the right way. So it should be very, very simple, right? But how do you prove it by induction? Okay, does anybody have any thoughts about how to do that? Yeah? Gamma comma A proves top. Okay, so the gamma comma A I agree with. And the reason it has gamma comma A, because A is down. In our translation, something with down ends up on the left-hand side. So we already know that much, right? We have to talk about A on the antecedent of the sequent. Okay. Now the gamma top, okay, I don't believe that, because you can always prove top no matter what your assumption is. Okay, so that's okay. So we know the gamma A. but what do we prove on the right-hand side? Yeah?
Gamma comma A proves C, then gamma proves C.
Okay. So unless you have seen the proof, okay, you just shortened my 5 hours trying to figure this out into 10 seconds, okay? Because this is indeed, if that and this, then gamma proves C. Okay, so what we're saying here is that if this gamma justifies the use of A, then this proof of C doesn't need to depend on A, because gamma justifies it. Okay? All right, so let's try to see if that works. Okay, let's see if it works here. Okay, so first, so to apply the induction hypothesis, we should have some proof of gamma together with A proves something. So what would that be? Actually, before we go there, in our translation, what did the down-up rule translate into? Anybody remember this? The what? Yeah, the variable which we actually called the identity rule. So remember this. The picture was this. Doesn't hurt writing this down. We have eliminations here, introductions here, and they meet at the down-up rule. And this corresponded somehow to like this, and we had the left rule, which were the inverse of the eliminations, and then the sequent arrow in here had the right rules, which were equal to the introductions, and this was the identity rule at the top. And the identity rule said if you have one assumption A, we can conclude A, right? Okay, which is called the variable rule in natural deduction. We call it the identity in the sequent calculus. Okay, so we should use the identity rule here. So then we have gamma comma A proves A by the identity rule. Okay, so now we have that, and we have this. Now we can apply the induction hypothesis to this derivation together with that. And what do we conclude? Gamma proves A by induction hypothesis on D prime and this proof that we have up there. But that's what we need to show because this is an up arrow. So we need to show that gamma proves A. Okay? All right. I'll do one more case because I want to see one example where the rules turn upside down. Okay. So what would be an example of that? Well, some kind of elimination rule. So case D is A and B down, A down, and elimination 1, and let's call this D1. Okay? All right, so we're trying to prove case 2, so we know just from the statement. Okay, so we're in case 2, so we know that, and we also know that gamma together with A proves C. So that's an assumption that we can use. Okay, just to write down, what do we need to prove at the end? So to show, what do we have to show? Yeah, gamma proves C, right? Hopefully we'll justify that, okay? Everybody along for the ride so far? Okay, this is our case. This is what we know. We're trying to apply, well, we suspect we need to apply the induction hypothesis somehow. How can we apply the induction hypothesis? So to apply the induction hypothesis, what kind of second piece of information do we need?
You know that if gamma A and B proves C, then gamma proves C.
Yeah, so it would be enough to show that if gamma A and B prove C, okay, then this would follow by induction hypothesis, right, if we had that. So it would be enough to show this, right? Because if you know this, then the induction hypothesis tells us If we know A implies B down and we know this, then we can conclude that. That's exactly what the induction hypothesis says. So the question is, how does this follow? That from gamma and A and B we can prove C. Because then we're done. Okay? So we know this. We have this derivation, this by induction hypothesis on D1. Okay, how do we know that gamma together with A and B proves C? Okay. By and left, the first and left rule. Okay. So that would require us to know that gamma A and B together with A proves C, right? From here, so it's now enough to show this. Because then this follows by the and left rule, and then this follows by the induction hypothesis. This is what we know. How do we get from here to here? Right. So there's weakening. Okay. So we extract that we need to prove some kind of a lemma about our system that says that if you have a proof, you can add an extra assumption that you never use. Okay. And still get a valid proof. Okay? So this has to be a lemma that we extract, that we prove separately, that we can always add an hypothesis and it propagates everywhere and we just never use it. Okay, so then we have this, then we get this by weakening, then we can use the and left rule to get that, and then we can get implied induction hypothesis because we have a proof for this in D1, we have this, and then we conclude that. Okay? And all the other cases are similar. There's no new idea in the rest of the cases. Okay? So the whole key was to try to come up with this generalization of the induction hypothesis to make the proof go through. Okay? Questions?
You need some base case for induction. All these cases are shown for induction hypothesis when we have some previous deduction.
Right. So there is this case that it's justified by something. So, okay, let's try that. So the derivation D actually is A down was justified as some kind of an assumption, which actually looks like, if you write it in this localized form, which I probably should have done here. Sorry. So if you have the assumption together with A, then we conclude A. Okay. So that would be the base case, right? Because we don't go above that. Okay. So what happens in that case? Well, well, we already used the identity rule. It would be strange if we used it more than once. The identity rule happens when the elimination meet the introductions, right? So here, there doesn't seem to be an identity rule. So actually, what do we also, let's just assemble our pieces, right? So what do we know by assumption because we're trying to prove a down arrow? So what are we allowed to assume? I think it's gamma together with A proves C. So that's our assumption, right? And what are we trying to show? What are we trying to show in this case? Okay, gamma proves C. Okay. Now, I was being sloppy here. Actually, I did the wrong thing. What's our real assumption? Yeah, that's because, okay, this is the left-hand side. So we really have gamma together with A proves C, right? Okay. And what do we really have to show? Not gamma proves C, but this left-hand side, gamma with A proves C. Okay. Now how do we get this? We get from here to here? Okay, by contraction. So we need a lemma that says that if you can prove in the sequent calculus C from 2 copies of A, then 1 copy to A is enough. Right? How would you prove such a thing? How would you prove this lemma? Of course, induction, right? Okay, sometimes people get so much in the mode of saying by induction that even if something's a two-line proof, they go and prove it by induction, considering 64 cases, okay? So you do need to sometimes think, put up your head, okay, maybe this is not an induction this time. But you can do an induction over the structure of this derivation, and what do we do in this induction? Well, let's say designate this copy of A. When this copy of A is used somewhere, we'll just use this copy of A instead, okay? So there's no reason to use a second copy, okay? So it's a very, very simple proof. Just like weakening is a very simple proof, because you just, by induction, you just add this X hypothesis everywhere, and that's it, okay? So fortunately, the lemma holds. But it is interesting, it's good that you brought up this case, because you think that the hypothesis rule should correspond to identity, but it doesn't, okay? In natural induction, the hypothesis rule, okay, corresponds to contraction, okay? And the down-up coercion corresponds to the identity rule, okay? And weakening we actually use throughout, okay? Okay? Okay, so this is how these kind of proofs go, right? So now I want to get back to my original program, which is to show that, I want to show that truth and verifications mean the same thing, right? A is true, so I want to show that A true if and only if A has a verification, okay? So from verification to true, this direction is very, very easy, because all we do, we're really restricting the application of the rules, inter from below or elimination from above. So the proof itself, so this is a very simple induction if you want to be formal about it. This direction is the tricky part. Because there are proofs here that you can't put the arrows on, right? Because the whole point was to restrict our rule of inference, right? In particular, we shouldn't be able to do that. A verification of B consists of a verification of A implies B and a verification of A, right? We have to remember that can't be allowed. So if you just put the arrows on that, this will be a proof, but it won't count as a verification if you go in that direction. Okay, so how do we go about doing this? Okay, so there's a number of strategies. So I'm going to follow the following strategy. I'm going to try to convince you without formal proof. If I add the following rule over here, okay, just for the sake of argument, if I have a verification of A, then I'm allowed to use A. If I added this hypothetical rule, then it would be easy to see that these two are equivalent. Okay, why is that? Anybody see why that is? Yeah?
Because now you might as well get rid of the arrows and turn up arrows into down arrows and down arrows into up arrows.
Exactly. So if you look at the rule over there, they already have the down up. We can go from down to up, and now we can go from up to down. So we can go back and forth. We can apply the rule by just going back and forth between up and down as we need it, right? So now it's very easy to see that an arbitrary proof can actually be turned into one with up and down arrows. But of course, we destroy the notion of a verification with that. So this is only hypothetical, okay, for the purpose of my proof. So if we had this rule, okay, then this would be if and only if. Now let's look at what happened to this rule in our proof, right? What would correspond to this in the sequent calculus? Okay. So let's do that here. So case D is gamma down proves A can be used if gamma down A up. Okay. Remember, this is hypothetical. Okay, this is not part of our original proof because we didn't have that rule, but now we do, right? I just want to see what would this rule correspond to in the sequent calculus. Okay. Okay. So what do we do? What do we assume? What do we assume? Because we're in case 2, in part 2. Yeah. So gamma proves. Now, gamma together with A proves C. So that's our assumption, right? And what do we have to show at the bottom? Gamma proves C, right? Do you see I'm setting up the case? All right, what do we get from the induction hypothesis to D prime? Okay, part I applies. What does part I give us? Gamma proves A. By induction hypothesis applied to D prime. Okay, so now we would be done with our proofs. We would be able to translate everything with up and down arrows, okay, into the sequent calculus if whenever gamma and A proves C and gamma proves A, then gamma already proves C. Then we would be done. If you can show this, right? So this whole thing here now becomes a lemma, right? If I could prove that, I would be done. Okay, so let me try to walk you through this again. A would be true if and only if this system with the additional rule, okay, this system with the additional rule we can translate into a sequent proof if you could close this gap. And we already know, well, you believe me, that we can take any sequent proof and translate it back into something in the original system without the up and down, without the up-down rule. So sequent proofs back, okay? So this lemma here is often also written as a rule, okay, which is called the cut rule. And the cut rule says, okay, if you want to prove C from gamma, one way to proceed is you prove some kind of a lemma A, and that gives you license to use A. And this is called cut, okay? And this is exactly, expresses the same thing that we express here, okay? In order to be able to use A, you have to find a verification of A. This is more economical in the notation, but it says the same thing. In order to be able to use A, we have to find a verification of A. Now this rule does not have the subformula property. In the sequent calculus, we always reason, we always construct our proof upwards, and we have to make up what this formula A is. It could be anything, okay? So if you want to use the sequent calculus for a proof search, right, then this cut rule could generate many possible cases for you, okay? But what this indicates, if my claim over there is true, if truth corresponds with the notion of verification, okay, then this cut rule should be redundant. So we shouldn't need that cut rule, okay? And that allows us to close the gap in that proof, okay? So this is the way that Gensen proceeded, essentially, with some variations, okay? So he basically said, I want to prove my system, my natural deduction system is consistent. I know how to translate natural deduction to the sequent calculus. In the sequent calculus, I don't need this rule. Rule is redundant, okay? That's what he called his Hauptsatz. People refer to it as a Hauptsatz, it just means the main theorem, right? But, okay, so that's his Hauptsatz, which says that we don't need that rule. If we don't need that rule, then, there can't be a proof of falsehood from no assumptions, because there isn't a verification of that, and then our system is consistent. Okay, so that was Gensen's program, and that's why he even invented the sequent calculus, okay, just for the purpose of that proof. Okay, so before I sketch how that works, are there questions on the overall program? Are we kind of on board here? Okay. So I'm not going to show you many cases of that.
If we have a disjunction in the proof of natural deduction, and
Yeah.
we have no corresponding rule in sequence calculus, so how can we
Nope.
translate this derivation?
No, for every rule over here, there is a corresponding rule over here. I'm sorry, between natural deduction and sequent calculus. Yeah.
So maybe there was no disjunction in natural deduction?
Now, there are three rules in natural deduction, right? The first introduction, the second introduction, then the or elimination rule.
Okay, and then sequence calculus
We have a left rule.
okay.
Yeah. It's just that rule, that weird rule where we have down arrows at the bottoms, that we want to rule out. We want to have only one elimination rule. Yeah. Okay, so by the way, these things are written out in the lecture notes, so you can look at them there. I mean, things go by fast, and you might have some doubts on some pieces of it, but it's all written out. Okay. Okay, so we want to prove the theorem, cut elimination. We prove admissibility of cut. And it states this: if gamma proves A, and gamma comma A proves C, then gamma proves C. And let's call this D, and let's call this proof E, and we'll construct some F which looks like that. Okay? So actually the proof I'm going to show you is one that I came up with around, I don't know, 2000 or so. And the way I created, actually, the way I came up with this proof is using the proofs as programs in reverse. Okay? I first wrote the program to take a D and an E and construct this F. Then I looked at the program and tried to figure out what it did and realized that it constitutes a proof, and I wrote down the proof. Okay? So I don't show you the program, but I'll show you the proof. Okay? Or at least the way it works. And the way it works is just by considering essentially all possible cases for what D and for what E can be. Right? So it's one of the various tedious things that you can think of. You just say, well, if D is that and E is that, we do this, and so on. And you have to make sure that in each case you can apply the induction hypothesis in some way to make something smaller. Okay? So before I say what the induction is on, okay, let's do a case in the proof and let's see what we can extract, okay, from the case to come up what the induction might be over, what might get smaller in the cases. So I only write down one particular case, okay, so this is, and the case I want to consider is where D is the right rule. Actually, I should say A1 and A2. Gamma arrow A1, gamma arrow A2, call this D1, call this D2. And E looks like gamma comma A1 and A2 proves C because we use the and left 1 rule. Gamma A1 and A2 together with A1 proves C, and call this E1. Okay. All right, so that's the situation. And what I'm trying to construct at the bottom, what do I have to show? Yeah, gamma proves C. Okay. Usually it's a good thing to remind yourself what you have to prove, just in case you stumble across it, okay? All right, so now the question is, we don't know the induction measure, but we could ask ourselves, if you think about this as a transformation from this and this to that, is there some way we can apply the induction hypothesis potentially? Okay, so what are the potential ways that we could apply the induction hypothesis, not even knowing what it is, okay? Any thoughts on what we might be able to do? So we're looking for something that's proven on the left, somewhere here, okay? And that's being used on in the antecedent somewhere over here, right? That's what we're trying to look for. Because it says if you prove something, then you can use it. Okay, so anybody see some potential things we might be able to do? Okay, so that actually gets way ahead of the game. Okay, so I just want to see, so you're already given a potential induction hypothesis. Okay, let me just write, instead of on the structure, let me see on A. But before we do that, let's just see what we might be able to do. So there was one suggestion that we could apply the induction hypothesis to D1 and E1. Okay, and that suggestion makes some sense because we have A1 here and A1 here. Everybody see that that could work potentially because here we have a verification of A, if you will, and here we have a use of A1. Okay, now that doesn't match exactly our induction hypothesis, so what's wrong with that? We have A1 and A2 still there, so the rest of the left-hand sides don't match. This is two things here, this is just one thing here, but here these two things are equal. So we can't quite apply the induction hypothesis here because it doesn't match it. What else could we do potentially? Where else do we see something on the left-hand side? Here, also on the right-hand side here of a sequent, and in the antecedent over here. Notice anything? Okay, so here we have a proof of A1 and A2, right, a verification of it. And here we have a use of it in this premise. Okay, so potentially we could apply the induction hypothesis using all of D, but just this subproof here. You see that? To cut out this extra copy that we didn't want. Does that make sense? Okay, so if I take this whole proof here, the whole thing, all of D, but only this part here, then what do I get? So I get gamma, okay, together with A1, proof C, by induction hypothesis maybe on all of D and E1. And the formula that I'm cutting out is still A1 and A2, so the formula itself doesn't get smaller. So A1 and A2 is still there.
How does this not have the same issue as before? Now we have an extra copy of A1 on one side.
Yes, very good. So when we do that, we have an extra copy of A1 here, which you don't have here. Okay. So how do we deal with that? Yeah, so we have this extra copy of A1 here. We'll just add it everywhere here. Okay. Saying we don't really need that extra copy of A1. We'll just add it. Okay. So it's really E1 plus the assumption A1 added into it. Okay. No, sorry, that was wrong. Where do I need to add it? To D? Yeah. Plus A1. Okay. So it becomes a little bit shaky. You have to justify this somehow, but okay. So if this is somehow legal, then how could we proceed now? Now we could take D1 and this, let's call this F1. Now we could get gamma proof C by, okay, induction hypothesis on the formula we cut out is A1, okay. The first subderivation is D1, and the second subderivation is F1, okay. But that's what we needed to show. So if both of these steps are justified by our induction hypothesis, then we should be okay. So we just have to see that in both cases something gets smaller. So in the first case, if you ignore this weakening step, what gets smaller? This second argument. This one stays the same. It's still the same formula. It's still the same proof here, modulo if we ignore this. And we have E1 is getting smaller, right? Okay? So it seems like two things are staying the same, one thing gets smaller. We should be okay on that one. So on here, what gets smaller, if anything? Well, D1 gets smaller, so that's good. But F1 here is the result of applying the induction hypothesis. That could be arbitrarily large, right? Because when you do cut elimination in general, you will get much bigger proofs than what you started with. So this could be huge here. So this could be much bigger than what we started with. But we're saved by the fact that this formula A1 is a subformula of what we had, right? So we do it like this. So we do it by, sometimes it's called a nested induction or lexicographic induction. First on A. Okay, so if A gets smaller, then the other proofs, what happens to them doesn't matter. They could get much larger. It doesn't matter as long as A gets smaller. And second, if A stays the same, then either D gets smaller and E stays the same. Oops. Or in other cases, you'll see D stays the same and E gets smaller. Okay. And turns out that this is a well-founded ordering. It's a lexicographic ordering. First, this is the first component, and this is like the second component of that. Okay. So at least in this case, it looks good. Okay, and I've done all cases, so yes, it looks good. Okay. Takes a leap of faith. So the only question is, can we add A1 to D and still apply the induction hypothesis to that? So if you count the size of the proof, let's say by the number of inferences in it, you'll see that if you add this assumption there and you never use it, the proof is still the same, right? So the size of it doesn't change. So that's why here we're still allowed to use the induction hypothesis, because adding an assumption everywhere doesn't change things. Okay, so this is the structure of the cut elimination proof. Okay. Now embedded in this kind of a proof is this kind of a local criteria for doing a reduction, okay, except on the sequent calculus. So if we didn't have this extra copy of A1 and A2 here, it would basically say if you have an introduction which corresponds to the right rule, and here you have a elimination which corresponds to a left rule, okay, then you can reduce that, and the way you reduce it is to this introduction meets this elimination here on the smaller proposition. And there's a little distraction here about getting rid of the extra copy of A1 and A2. Okay. So we'll see this when we get to the linear logic, that we can apply local tests also. The thing is that the local test does not imply global cut elimination. So there's cases where the local tests succeed, but when you try to prove it for the whole logic, then it will actually fail. Okay. And I don't know of any general theorem on how to extend the local test to the global test. Maybe Ed, as a category theorist, knows how to do that. Okay. Here you actually have to work very hard, okay, to go from the local test and then make sure that globally cut elimination holds. Okay. Okay. Before I move on, are we okay with the structure of all of that? Okay. What I've shown you now, okay, well, I've shown you small pieces of this argument that if A is true, A is true if and only A has a verification. And the tricky part of that, A is true in this direction. And this direction is obvious. This direction is hard. Here's how you do it. Let me talk you through it again. If A is true, then it has a quasi-verification, let's call it. We use this additional rule. Okay. From there, okay, we can go to a did I erase that case? Okay, we can go to a proof that doesn't use that rule by translating, okay, according to our theorem, where this rule turns into a cut. And then here, by the admissibility of cut, is we don't really need it. And then we can translate the corresponding cut-free proof back into something that really is a true verification, not using this bad rule anymore. Okay? And therefore, we get a good verification out at the end. Okay? Okay, so that's our roadmap. There's other ways to do it, but this is one that gave me a chance to show you the sequent calculus. Okay? Questions? Okay. Yep.
You said that you came up with this particular proof by going through a programming language.
Yeah.
The programming language, so we showed how correspondence between, particularly calculus and natural reduction. Do we have the same correspondence here in sequent calculus? Does that just sort of transfer over in the direction?
So are you asking whether there's a programming language that corresponds to the sequent calculus?
So, yeah, you mentioned you went through a program, right? Does that program look like the one that you would have done in natural?
Okay, so this program is written as a function which takes a proof D and a proof E and returns a proof F. Okay. And so that's in a meta language. It's not inside these calculi. Okay. It's written in a meta language. So I wrote it in a logical framework called 12. Okay. And the logical framework is a formal meta language in which you can formalize and reasoning about deductive systems, like natural deduction and like sequent calculus. So what I started is, well, I did all of these proofs today in that. So I formalized natural deduction by some rules. I formalized the sequent calculus by some rules, and then I went through the steps that I did on the board, but writing down all these things as programs in the logical framework. And the logical framework checked, yes, this is a proof. So it told me, yes, A is true if and only if A had a verification. But that proof that I did was not known in the literature before. And so I looked at the code very carefully and I extracted what I just showed you.
Okay. Okay, so the other part of that, right, so it sounds like there's not so much a direct kind of correspondence between the way that we have between typically cyclic calculus and natural deduction.
Yeah.
There's not such a direct correspondence between Lang and the sequent calculus. Is that right?
Well, people have worked on that.
Sure.
It turns out that, well, you will see in linear logic there is a really good correspondence between a linear sequent calculus and blank, okay, which I'll show you the rest of this lecture and the next lecture. For this one, for the intuitionistic one can construct also correspondence. But if you do it completely as an isomorphism, it's not something that you would want to program in.
Does it have, I guess, does it have a name for a intuition? Like, the way that you call what you get from natural deduction functional programming.
Yeah. So it's still functional programming because it's still, you still build proofs, but you, okay, I guess I'll have to show it. Okay. So let's look at this as an example, okay? Gamma, and you have x colon a1 and a2, and you want to ask what kind of proof term could I have for x colon a1 and a2, y colon a1, proof C, okay? So I'm going to do a proof term assignment which is faithful so that I can actually see, okay, so what does it actually do? It would say let y equals pi 1 of x in some proof term m if m is a proof of that. Okay, so x is going to be a pair. So pi 1 of x, if I reuse the same notation, would be the first component of the pair. And so this term m can mention both x and y. Here I have bound y because it's bound by a let, and I only have x occurring free. So each elimination form corresponds to a let where you extract a minuscule piece of your overall term from what you're computing with. Okay, and you can do that for all the left rules. And the right rules just form like pairs and functions, just like before. The right rule looks pretty good. The left rule just proceeds in really small steps. So your whole program is a bunch of like let. Okay, so if you really want to stick to that literally, it's not very nice to program in. Okay, that makes sense to everyone? You'd have to have a really good reason to use just this notation, and you get fed up pretty quickly. Okay. But it's still a very interesting subject because people have devised many variations of sequent calculi. So for example, remove redundant assumptions and so on. It's a whole area in itself to streamline the sequent calculus. And then the programming languages come out of that are really interesting actually. But if you take the pure one that comes directly from natural deduction, it's not super useful. Okay, yep. Yes. Unfortunately, it's not really a normal form because you could. Yeah, because, yeah. So.
If you change that one in the application rule, if the A had to be down, would that ruin anything?
No, that particular thing is not so bad, but You can enforce a normal form with the sequent calculus, but just not this one. Okay, so you have to do some transformations. And then various things that people have sort of in ad hoc discovered before, you can describe as variants of these inference systems. Yeah. Okay, so let me go to linear logic then. So one of the reasons I spend so much time on the sequent calculus is that with linear logic, I'm going to jump right into the sequent calculus. And of course, there are also natural reduction presentations, but they're not quite as useful and not quite as easy to appreciate. Okay, so linear logic. Okay, so in this translation up there, you saw that we need weakening contraction in order to make the correspondence between natural reduction and sequent calculus. Linear logic, at some point, it's in some way you can think of simply as arising when you take away weakening and contraction. Okay, so if you have something like this, A1, AN, proof C. Now I should invent a new symbol. Maybe I'll just write turnstile because, okay, forget everything I've said in the first 4 lectures, okay? Should be easy, right? And so this now means we're in linear logic, these things are your assumption, but we're in a sequent calculus, okay? Okay, and the point is that these assumptions here, you think of these as being resources rather than logical assumptions. Resources, which means that you must use them exactly once. Okay, so in the proof of C, you must use all the assumptions, and you must use them, and you can only use them once, not multiple times, right? Exactly once. Linear logic is extremely pedantic, okay? If I want at most once, then I get affine logic, which is also interesting, but I want to talk about the linear case, okay? Now, yeah? There is some reason for that, and I guess you'd have to go back to Girard's original paper to look that up. He makes some case about where that comes from. Yeah. Okay, so this seems extremely weak, right? There are very few things you can prove if you can use the assumptions only once, right? Or must use them exactly once. So it seems like, oh, your logic is really, really weak. You can't do very much. And for some time, people have worked on various restrictions of intuitionistic and classical logic way before Girard did his work. So this, by the way, goes to Girard's seminal paper in '87. Okay, so various people have worked on that, but there was no interest in it because it was really, really weak. Okay, and so the question was, well, what do you do with such a weak thing if you can't even prove all the things that are intuitionistically true, right? Intuitionism already was considered, oh, that's too weak. And there, you have to use all assumptions exactly once. So Girard's insight was that, and actually it goes back to also something Bob said, okay, we introduce a modal operator called bang. Actually, he calls it of course, even though it's usually pronounced these days bang. So of course A means now you can reuse that. Okay, so the modality gives you the opportunity to reuse things multiple times. And that's strong enough now that you can take intuitionistic or classical logic and embed it back into this calculus. Okay? So you make a restriction, assumptions must be used exactly once, and that's really powerful, but in order to not lose any expressive power with respect to what I had before, there's a particular way to indicate that something is reusable. Okay? And that's, people had considered this before but not realized its importance. Okay? Especially not in combination. Okay, so what happens is that when you make a logic weaker, in this case by restricting weakening contraction, you get this paradox that you have more connectors, you have more expressive power, you can say more things. So for example, you might say classical logic is just defined by, let's say, on the propositional case by, let's say, or and negation. I better call it and negation, okay? And you don't really have, so this is classical logic. In intuitionistic logic, you have conjunction, and they kind of agree. You also have a constructive disjunction, which doesn't exist in classical logic. It doesn't exist because there's no way to express that you must be able to prove one or the other, right? Because the law of excluded middle holds here, and here it does not. And then you have negation, which is similar to this one here, and you have implication. And the intuitionistic implication doesn't really exist in classical logic because in classical logic, A implies B is equivalent to not A or B. And that's equivalent to not A and not B, whatever. So you can express it just by using, whenever I do classical logic, it's wrong, but yeah, because it just doesn't make any sense. But whatever, okay. You don't need implication, you don't have implication, but here we have implication that says you make the assumption that you try to prove B and it's well scoped and all that. So you gain two new connectives here, the or and the implication. And when we go to linear logic, we gain some more connectives, which is really an interesting phenomenon. So we have what we had before, but we also gain some new connectives, and I'll try to show you what they are. And then in the next lecture, I'll talk to you what they mean computationally. Okay, so it's not just a logical game, but it's a computational interpretation of these things. Okay, so where did we start? Okay, so one way to start is just to, okay, so I'm going to write these things here as delta. Okay, and the reason I'm going to use delta instead of gamma to remind you that things in delta have to be used exactly once. Okay, so that's why it's different letter. Okay. So the first thing we can do is we can internalize this notion of linear entailment as a proposition. Okay, so here's how we do this. So in delta, we can prove A linearly implies B. Okay, usually this is pronounced lolly because this looks like a lollipop on its side. Okay, if we add the resource A to our context and then we conclude B. Okay, so this is the lolly introduction. So the way to read that is, if I only had the resource A, I could achieve my goal B, okay, with these resources. It looks like implication, but remember that this A here is very restricted, okay? Okay, so actually I should say this is a right rule because we're in the sequent calculus. So the question is, what should be the corresponding left rule if I know A, B, and I'm trying to prove C? What should be the left rule for that? Okay, so we can take an analogy with the previous idea. So if I could only find a way to achieve A, this tells me if I had an A, I could get a B, so then I'm allowed to get a B, and then I can conclude C. So this would be the lolly left rule. And I only have to worry about what happens to my remaining resources. And the remaining resources are split into two. Okay. Okay, so this is a little shorthand. I take the remaining resources and I split them into two. The order still doesn't matter. Some of these resources go here and the other resources here. So that way I can guarantee that all the resources here are used exactly once. This is used right here. These here will be used here, and the ones in delta will be used here. Okay, makes sense? Okay, the identity rule, which I should talk about. So previously, okay, I allowed some kind of side formulas here. Now, the identity rule is exact. Okay, it's just from A you can get A. Why would it be wrong to put a delta here? Because I said I was pedantic. Because we wouldn't be using them, right? I'm supposed to use all the assumptions, so I can't allow the delta there. So the identity rule. And also, when previously in the intuitionistic logic and the sequent calculus, I said we have to copy this formula because we might use it again. Here we absolutely, definitely do not copy this formula because we're not allowed to use it again, right? Use it once and it disappears. Make sense? Okay, so this is linear implication. The next connective I want to have is, let's have one theorem about this. Can somebody think of a theorem with linear implication? A lolly A, excellent. Okay, so that should be true without any assumptions. How about this thing? Should that be true without any assumptions? No, because I can only use this one or that one, but not both. Okay, so that has not to be true. Okay, good. Now the next thing I can wonder about, what logical connective would correspond if I had that comma on the left-hand side? What would that be? Okay, so let me write it with the left rule first. So if I have delta and I have A and B, and I try to prove C, the way I put them together is with an operator called the tensor. And this is the tensor left rule. Okay, so A tensor B means that I have both A and B, okay, in the same context. Right? I get both A and B out of that. So what's the corresponding left rule? The corresponding right rule. So the tensor right rule. Well, you can see it corresponds to some form of conjunction, right? Because I split that up into the two pieces. By the way, unlike the other conjunction, intuitionistic logic, you don't get just one part of it, but you get both of them at the same time, right? Okay, so what is the right rule corresponding to that? Okay, so we have A tensor B on the right. And how do we break it down? Well, it's a kind of conjunction, so we should be able to prove these. Okay, we only have to worry about what happens with the resources here, and we have to split them, right? So we devote some of the resources to proving A, the remaining ones to proving B, to prove A tensor B. Okay? All right, so let's think about our local test that these rules fit together. Okay, so what I want to do is the following. I say if I have a right rule meeting a left rule, can I apply some kind of a reduction? Okay, so the way it's going to look like is delta proves A, call this D, and delta prime proves B, call that E, and I get delta together with delta prime, prove A tensor B, and here I have delta 2 prime together with A tensor B, prove C because delta 2 prime, and A and B prove C, and let's call this F. So that's a tensor left, and this is a tensor right. And now I have a cut here, and the cut is of the formula A tensor B, and I end up with delta together with delta prime together with delta double prime proof C. Okay? And so the test I want to apply is, can I reduce this proof so that I don't need to introduce a tensor but still come up with the same conclusion here? Okay? So the question is, can I apply cut on smaller formulas to get the same conclusion, and that would justify the conclusion? Okay, any idea what I could transform this into with a local reduction that's sort of like the reaction we had before? So can we justify this conclusion? Okay, so what we're looking for is cuts with smaller formulas. So here prove A, here use A. Right? So we can do a cut between D and F. And here I prove B, and here I use B, so we can also do a cut between E and F. Right?
So we don't have a cut rule in this logic order.
Okay, so you can think of it two ways. Either we're trying to show that something can be justified by cut, can be justified in simpler versions, or we just add the rule of cut, and we have a global theorem that says we never need it. So let's assume we have the rule to keep it simple. Okay, so the way we're going to rewrite this is we're going to take D with delta and A, and cut this with delta double prime A and B proves C with F, up F. This is a cut, and the cut formula is just A. And we get delta, delta double prime, and B proves C. And then we cut this with E, which is delta prime proves E up B. We apply another cut. And this is cut formula B, and we get delta, delta prime, delta double prime proves C. Okay? So we reduce one cut of A tensor B into cuts on A and B. And that's an example of a reduction. Okay? And it's local because whatever D, E, and F are don't matter, okay, in this check. But this local is going to be part of my global cut elimination proof. Yeah?
For the, could you just repeat it in a sentence what the lottery right rule? Take that into
Okay. So with the resources delta, I'm trying to prove that A implies B. And I can do that if I assume I had the resource A, I could prove B. That's the meaning of the implication, the linear implication. So it's like an ordinary implication, except the assumptions can be used only once. By the way, if you want the intuitionistic implication that we had before, that would be expressed as bang A linear implies B. Okay? Because bang A, once you put it in the context, you can use it as often as you want. So it gives you a license to reuse that. So that's somehow like A implies B. Okay? But here, just use it once. Yep?
Can I see that we are using the resource case to show B?
Yes. To have a proof, we must use it.
Because in the other logics, there was, it may or may not use it.
Exactly. So linear logic is distinguished by the fact that you must use the assumptions, and you can use them also at most once. So together it means you must use them exactly once. So there's no slack, okay? So in particular, there's nothing allowed here at the identity rule. Okay, so what this reduction over there shows us is that the right and the left rule here, they fit together appropriately, and we have such a test. If you know, yep.
So how the bottom line on your Sequent map,
Yeah.
is that, are you supposed to have,
Sorry. Yeah. Otherwise, we would have duplicated resources, which is not good.
Did a proof have two copies of the resource two copies? Does that ever happen?
Yeah, that could very easily happen. For example, I would claim that the following should be true. A implies that A implies, can you complete this? Yeah? Yeah. Right, so that should be true. Okay? Yeah?
Can you talk, what's the thing around banding and explaining all the A?
Yeah.
The A plus B?
Yeah.
Why isn't it, why is something on A always B instead of?
Okay, so the question.
Like, you have to prove bang A. You only have one A. You can't get anything.
So what this is, you assume bang A, and assuming bang A means you can use it as often as you want in order to prove B. That's why I put the parentheses. So to prove that, okay, you assume bang A, try to prove B, and assuming bang A means assume as many copies of A as you need. So that's why parentheses are like that. But it turns out there's a different translation where you do it like that, and for reasons I don't want to explain, that also works. Okay, I find this very much less intuitive than this one, but Girard describes both of them. Yeah?
Could you explain again the last board part, the last one you can do in the theorem?
Okay, well, let's prove it. Let's prove it. Okay, so instead of explaining it, let's prove it. A arrow, A tensor A. Okay, so we assume A. We now have to prove A goes to A tensor A. So we assume another copy of A. And now we have to prove A tensor A. So this was lolly right, lolly right. At this point, we want to apply tensor right. And on the one side, we prove that version of A. On the other side, we prove that version of A. Right? Now, we have to split our assumptions. Some part has to go here, some part has to go here. Right? We can't put both copies of A here. If we do that, we'll be stuck here. We can't put both copies of A here. So one copy of A has to go here, and the other copy of A has to go here, and this follows then by identity, and this follows by identity. Okay? By the way, how many proofs are there of this? Does anybody have an idea? There should be 2 proofs, right? And it depends on whether this assumption goes here or this assumption goes here. The other one is forced, right? So there's 2 normal proofs without using cut. Normal proofs, I should say. Yeah? Yeah, that's, we don't track the identity, but once you care about the structure of proof and your proof terms, right, then these would be labeled with X and Y. And you would have a proof X, or you would have Y going here and X going here, right? So the pair here that you get out, the pair for that, would either be the pair XY, or it would be the pair YX, right? So there would be 2 different ones. So once we look at the fine structure of the proofs, then they become different. Yeah. Okay. Yeah?
So that means that properties we saw before, like construction, would not hold.
Right, they would be wrong, yeah. Right, and weakening as well. They are not valid proofs, yeah.
When you have then A, does that mean that you can not necessarily use A, or does it use it at least once?
Okay, you don't have to use it at all. Yeah, because in linear, it has to be that way for this embedding to work, because in the proof of A implies B, we don't have to use A. So that also means we don't have to use that. Yeah. So I'll come to that tomorrow, because I'm out of time now. But if there's any more questions on this so far I've only shown you 2 connectives, but there are more. Yeah.
When you were talking about the affine logic and you referred to a paper,
Yeah.
could you just maybe set that on the piazza, or do you know, or at least the author?
Okay. Okay, other questions? All right, so what I'll do tomorrow is I'll complete the connectives. Wait, is this lecture 3 or 4? 4, okay. So what I'll do tomorrow in my last lecture here, okay, I will complete the connectives and I will sketch hopefully enough of the operational interpretation for you that you can go off and read the rest. Okay. All right.